right. In this worked example, we're going to be looking at an idea that we introduced at the beginning of the year with base units, but related to sort of the current ideas of work, energy, and power. And so the question is, determine the SI base units of power. It's always good to start with an equation that contains that. So let's say power equals work over time. Just to be very thorough and to use this question as a problem study to sort of get all the physics we can out of it, let's review some of the derived units that are contained herein. And so watt is the unit of power, not a question, that's a statement. Watt is the unit of power. Now, if I just put W for watts, it's like, well, this W stands for work, but this W stands for watts. And you can clearly tell the difference, right? So I just, to make it clear, I wrote it all out. I also like a convention where I'm going to put all the units in parentheses, and quantities won't have that. So like power is a quantity, work is a quantity, time is a quantity. Watt is the unit we measure the quantity power in. Right? So just, part of it is just getting used to the language, the academic vocabulary. Work is measured in joules, and time is measured in seconds. Now I wrote it even out, SEC for seconds, because as I expand the definition here of work, force times, we use the letter S for displacement in physics, right? So it's like, well, this S is different than that S, right? Just like this W is different than that. So we get this here. So it is true that a watt is a joule per second. Okay, 1 joule per second is a watt, but a joule is a derived unit and a watt is a derived unit. The only base unit we've got so far is the second. So by expanding sort of the definition of work, right, that's the units there to keep with my convention up here. We said that, well, work is force times displacement. All right, and so a joule is really a Newton of force times a meter of displacement per, and I'll just put an S here for seconds of time. So a Newton meter per second is the same thing as a watt, is the same thing as a joule per second. But we still don't have base units, right? This Newton is still a derived unit. So let's give ourselves another equation up here. Force equals mass times acceleration, to remind ourselves that this Newton is really equal to kilogram meter per second squared, right? So kilogram of mass times meter per second squared of acceleration is the derived unit, the Newton. So plugging that in for newtons, we get kilogram meter per second squared, right? That's just the Newton. We still have another second down there in the denominator from that, and another meter up there in the numerator from there. Putting it all together, we can report our final answer as kilogram meter squared per seconds cubed. So the base units of power, I would just commit that to memory. I'll just memorize that right now. Power is kilogram meter squared per second cubed. It is today as we think about it. It will be tomorrow, and anytime in the future you're ever asked to solve for the base units of power. Time easy goes. All right. Now the question goes on to give us figure 1.1 showing a turbine that is used to generate electrical power from the wind. Okay. And the power P available from the wind. That's important, that this is the power available from the wind. And it's given by that equation there. And they've defined all of those variables for us. Our job now is to show that C has no unit. So it's similar to what we just kind of did. But now we have to look at what the idea called homogeneity in the equation, sameness. So we need the same units on each side of the equation for it to be valid. Showing that the equation is homogeneous in terms of the units does not prove the validity of the equation, but it can disprove it. Okay, so if the units aren't the same, we can immediately disprove that equation. So nope, the units aren't right, it can't be right. And it looks like C is just some dimensionless constant. So really what we've got is one calculation leading to the next. Don't forget that we just figured out what the base units of power are. So like we know the left side. It suggests that because C is dimensionless, has no units, that the units of L squared rho V cubed should be the same as power. All right, so let's kind of prove that now. All right, we've got this equation. I'm just going to kind of look at it up here instead of rewriting it. So the left side is going to have units of kilogram meters squared per seconds cubed. Right? I know it because it's power, and we just solved that the base units of power are that. we'll just go right to those base units for the left side of the equation. I will leave C as a C, but kind of put it in brackets to remind myself, like, that's the thing that should just be left alone. If we can show that the rest of it is equal to this, then yeah, C won't have any units because we just multiply nothing by all the rest of it. And, you know, it's not like it's 0, it just has no units, right? So it has some value, but it doesn't have any units, okay? So let's go through it now. L, they say, is a length. And so if we're substituting in for L squared, then the units there are going to be meters squared, right? So length measured in meters, but it's squared, so meters squared units from that. I dropped the parentheses because all I'm working with here are units, right? I guess besides C, I put it in brackets. All right, rho, density. Anybody remember what density is? Heard everybody say in unison, mass per volume. I don't think the mic could pick it up, YouTube, but the whole class said it together. Mass per volume. And we know that mass is measured in kilograms, and we know volume is measured in length times width times height, meters for all of those linear dimensions. So cubic meters for volume there to be the base units. Cubic centimeters, right? Makes more sense when you're doing chemistry, right? We're weighing things out, milliliters, cubic centimeters, but the, you know, a cubic meter is pretty big volume, but it is the base unit. All right, so we're going to substitute that in for density is the next term. So we got kilograms per meter cubed. All right, and then we got velocity cubed here. So velocity is meters per second, but because it's cubed, we need to cube all the units too. All right, and so it should be that once we combine all of this, we get the same thing over here. And can already sort of see it. Well, there you go. Like these, we'll cancel those. That's kind of nice. We just got kilogram meters squared per second cubed. Kilogram meters squared per second cubed. There you go. Or you could have combined these two instead of all meters to the 5th in the numerator, and 3 of them will cancel out, leaving 2 left over. Whatever sort of makes sense to you. So because we have kilogram meters squared per second cubed on this side, we have kilogram meters squared per second cubed on that side, just from the product of L squared rho and V cubed. You know, we can kind of leave C like, hey, it didn't need to do anything, right? Therefore, C has no units. Good. If you needed any of that for a moment or two longer, pause the video, go through it at your leisure, or even rewind it. But I'm live right now in class, huh? Too bad, you gotta take a look on YouTube later, class. Don't forget to smash that like button, leave a comment, get on the Dr. Schleich notifications box. All right, now we've got to calculate the wind speed from some values there. So let's remind ourselves of this monstrous equation. Power equals some constant C, which they give us the value now with no units with that one. It was L squared, there was a rho in there was a V cubed in there. That was it. And they tell us the density of the air is 1.3 in the SI units. They don't give you any clue as to what those units are because they want you to know it for the previous calculation. Well, in the SI units, here's the density. They give you the meters, you know, for length. They're like, okay, we'll give you that freebie. And then there's the derived unit, the watt per power. Now, efficiency, we were introduced to this idea the other day, but we haven't really worked with it too much in terms of calculation. So we have the efficiency of the turbine is given as 55%, and they give us the power output. Remember that they define power in this equation as the power available from the wind. Like the wind has a certain amount of power in it, but this machine, this turbine, is only 55% efficient at converting that available wind energy into like useful energy out. All right, so you could sort of rely on the definition of efficiency as like useful power out over total power in, and sort of just calculate it that way. I like to think about it kind of like a word problem where, you know, we could say what number of available sort of wind energy, when I multiply it by 55%, gives me this output power. You know, if you kind of talk your way through the word problem like that and convert that language into mathematical symbols, you'll find that that's a good general problem solving strategy to solve lots of different questions, not just in physics and science and math, you know, but other questions too. So I want to say, what number, when I multiply it by 55%, is 3.5 by 10 to the 5 watts, right? So that's sort of the way I can set up the calculation. How much power is available from the wind if when I take 55% of it, I only have this much sort of available power output, or I've only generated that much power. So mathematically now I can divide each side by 0.55. And then you could think to yourself, if I divide by a number less than 1, what happens to my answer? It's bigger, right? And it should be bigger, right? Like there's more energy in the wind than there is output power because my machine is not more than 100% efficient, just like any machine. You know, like no machines are more than 100% efficient. So we've lost some energy. And if you can kind of preview what's to come here, part 3 of this says suggest 2 reasons why the electrical power output of the turbine is less than the power available from the wind. So we're gonna have to sort of give an explanation for this in a moment. But right now we can just sort of quantify it. I'm gonna change my question mark to a P for power here, because this will be the power available, right? Like that's the way they define this power. This P right here is the output power. They italicized it or something to distinguish it. So in your calculator, you can do 3.5 by 10 to the 5 divided by 0.55, and I think you get 63 repeating. So 63, 63, 63.6. That many watts of power. Okay. That's the power available in the wind if we're getting an output power of this, and we know that the turbine is 55% efficient. Right? You kind of say like, wait a minute, you're saying the wind has this much power, but we're only getting this much out of it? Why? Well, you'll have to explain that here. Why don't we get all of the power of the wind out? All right, so then we can plug this in for P, but before we do that, I think we should isolate V because it's asking us to calculate the wind speed, and that's what V is, right? So I think everybody's good with just saying, well, V would then be power over C L squared rho to the 1/3, right? I'll go with that. So just dividing each side of this by everything that's not V, you know, so divide by CL squared rho. That's why it's all in the denominator over there with P. And then taking the cube root, so like isolate V because it's V cubed, you got to take a cube root. Taking a cube root is the same thing as raising something to the 1/3 power. I think that's just easier to type in your calculator. Got a good cube root. It's equivalent to say like the cube root of all of that. Okay, like if you like that symbol, you know, a cube root, don't have to use those too often. It's always a square root, you know, take a cube root. But my preference is again just to kind of raise that to the 1/3 power. Now let's substitute in some values. So we've got this for the power. So it's going to be 63636.6. That's probably enough significant digits. Over, they give us C as 0.931. They give us the length as 25. We already know the units are going to work out to give us meters per second because we've already dealt with, you know, sort of units at every other step, you know, in this problem. And then they give us the density as 1.3, and we even knew that the units were kilograms per cubic meters. I think we've got it all there, and so don't forget to raise it to the 1/3 power or take a cube root, whatever you kind of prefer there. And then who's got the answer, who's willing to call it out, who can calculate that? Go ahead, YouTube. Go ahead and raise them. Well, no fair, they had a head start. They were doing this live. I'm watching this centuries into the future. How could I possibly, you know, beat the students to the calculation? Well, just see, like if you start now, would you beat them to it? Come on, YouTube. I believe in you. What do you got? Why do you think you did it wrong? It's 9.4. So if you did something wrong, it serendipitously got you to the right answer. Or it's probably more likely that you just did it right. There you go, 9.4. If you're getting 9.4 out there, awesome. There's probably no incorrect way to accidentally get that. Maybe. I just put 9.3 in my calculator and added 0.1 to it. Like, no, that was serendipitous. That's not the right path to the solution. Crunched all these numbers and get 9.4. That's a good answer. If you're attempting that calculation, getting anything else besides 9.4, call me over there and we'll figure it out. You know, like every calculator is a little bit different, but you want to build your confidence that you can do these calculations correctly by practicing in class or practicing on YouTube and getting the same answer. Okay, I'm preparing myself for this ACE physics exam. 2 reasons why the electrical power output of the turbine is less than the power available from the wind. I'll leave that to you to consider. But just keep in mind the things that we talked about with efficiency, that nothing can be more than 100% efficient. And the idea of like last week's quiz with energy losses, right? We saw some energy losses due to wind. And so just kind of reason your way through that as best you can and brainstorm maybe some possible suggestions as to why this number, 3.5 by 10 to the 5, is less than this number. In fact, it's only 55% of it. What sort of happened there? This has been another work example with Dr. Schleich. We'll see you next time.